All right, so picking up where we left off with our slope fields last time, now what we want to do is approximate some solutions to the differential equations, kind of following on that theme. But instead of separating our variables and using integration, we're going to use a numerical strategy for doing this, called Euler's method. Now, the way that it works is that we would have a differential equation. For example, maybe we have our population model here, and we also would have a starting value. So it's an initial value problem. And we're going to use these two pieces of information to approximate solutions to the differential equation without actually solving this differential equation analytically. The way that we'll do this is just by using little tangent lines. We're going to walk along tangent lines for set intervals. And this value h in Euler's method defines how far we step for each approximation. And however far we step, we're going to make that much change. This expression here represents the value of whatever the derivative is at that point. So in our example, we start at this point, at time 0, we have a population of 1. And we also know from our differential equation that we're changing at a rate of 1.1 when the population is 1. So according to Euler's method, what that means is that our next approximation for y is going to be, so like right now we have that y0 is 1. And Euler's method tells us that our next approximation is going to be whatever our previous value was, so 1, plus, and again, we're going to take a step of 1/10. So 0.1 times whatever the value of our derivative is evaluated at that time. And so this, happens to be when p is 1. So it's 1 plus 0.1 times 1.1. So instead of this, we can just think about times 1.1. And then y2 would be whatever we get here plus 0.1 times whatever the value of the derivative is at y1. All right, so, and we can just continue to update. And really what we're doing is we're just kind of walking along tangents for 1/10 of a, and drawing little line segments each step. Okay, so this is the big idea, but let's now actually implement it. So using this same differential equation, where we have dp dt equals 1.1 times p, and we have an initial value at 0 of 1, I've just defined a function to be that derivative will start at 1, and I'm also going to keep track of my x's, and then I'm just going to take 9 steps ahead. So we'll have a total of 10 values for y. And our next approximation is just the last approximation plus whatever our step size is. So here again, we've said that it's going to be 0.1 times the value of the derivative at that previous y value. So steps -1 is always going to take the last element of this list, or the last y value is what we're using here. And then we'll take whatever our next approximation is, we'll pop it on that list, and we'll just continue to do this over and over again. I also want to keep track of my x values so that we can plot this easily. But if we run this, then we see here over those first 10 approximations are the values of our population, approximations for our population. And we can go ahead and look at this with a slope field. And what we see is our line is roughly following, each of these are our little tangent lines. And it does seem to be roughly following the behavior of the larger slope field. And what's really nice about this is we can just take our differential equation and replace it with any other differential equation. The big idea is just this, that our next approximation is whatever our last approximation was. We take a step and we multiply it by the value of the derivative at that last approximation. So we could look at a problem like this with Newton's law of cooling. Okay, and if you imagine a hot potato cooling in a room, just run. Now, in this case, what I've done is increase the number of approximations. We make a lot of approximations here, 300 approximations. And we take a bigger step. We take a step of 2.5. And let's see what that ends up looking like. All right, that makes sense. It seems that the hot potato or the pizza, actually this was a pizza, this is a problem from OpenStax. The pizza cools down to the room temperature. We saw this logistic equation before. Same idea, we just changed this differential equation. Everything in the actual approximation strategy remains the same. This time we're taking 30 steps and a little bit bigger, 0.2. And sure enough, we see that expected shape. So Euler's method, very powerful, but some issues are, we're going to have error here because we're just making approximations, and depending on how small or large of a step size is, that will change, and it will also be a trade-off in computational energy to make these approximations.